Right, so we are starting what is considered called our sampling distributions. So we're actually going to look at two of them. We're going to look at sampling distributions of means and one of proportions. That being said, there are several other sampling distributions that we have that they could be variance, standard deviation, a variety of other things. We're just looking at two of them right now. So sampling distributions are going to be pretty important for us because we actually use sampling distributions for a lot of the stuff that we have going forward, mainly doing confidence intervals and hypothesis testing. Sorry, I have a problem talking. Uh, so those are the two, like the big things we really like to get out of statistics, and we're going to start pulling those apart right now after talking about a sampling distribution. So I'm going to go to this applet as well. So we're going to see a little bit of bouncing. So I left a link in the PowerPoint or the PDF version of the PowerPoint anyway, so that you could pull this out if you wanted to play with it as well. So in real situations in statistical studies involve sampling several individuals, then computing a numerical summary of the sample. And most often, the numerical summary that we like to collect is our sample mean, our X bar. So if we collect several samples, because as we see from the law of large numbers, doing something once is not as dependable as doing something several times. If several samples are drawn from the population, so I have a whole bunch of samples, they're likely to have different X bars. Like we expect any two samples, doesn't matter if the same sample size or not. If I collect two different samples, they're not likely to have the same mean. They're likely to be a little different from each other at the very least. Because the value of X bar varies, and we mentioned this before, varies each time a sample is drawn, X bar is what we can consider a random variable. So what we're doing here is we're still looking at a random variable. So far, a random variable has just been an X. So it's been an individual data point. Here, our random variables are going to be means from random samples. So for each value of a random variable, X bar, we can compute a probability. The probability distribution X bar is called the sampling distribution. So what we've been doing, oops, let me fix that. What we've been doing is collecting individual X's and making a sampling distribution of them. What we're going to do now is instead of just individual X values, we're going to collect a bunch of samples. So we'll collect a sample, like several different points here. So X1, X2, X3, X4, let's say that's my sample. There's going to be a mean associated with this sample. So we'll call this the first mean that we have. And the same thing again, if I collect another sample of a couple different X's, I'm going to get a new mean. And that's going to have a different mean. So we can make another distribution that's just simply distribution of different means that I get. So this is what we consider to be the sampling distribution of X. So this is just a distribution of a sample or distribution of just X. This is a sampling distribution of X bar. Like I said, it's along the same ideas. It's just that when we start talking about probabilities or what these values actually mean, there's a slight difference there. But a lot of this is very similar to what we had before. X bar is a random variable. It's just we have different means. My means are my random variables. They can be continuous, so we're going to treat this like a continuous distribution and use those things that we had before with z-scores and probabilities to gather information about the data. So far, nothing is too exotic or new here. But let's talk about what we're doing when we talk about a sampling distribution. So a tetrahedral die has got four sides to it. So the faces are going to be numbered 1, 2, 3, and 4. So if each face corresponds to, like I said, number 1, 2, 3, or 4, and tossing a die, we are going to get a sample population looks like this. This is my sample space. So my sample space is either I roll a 1, a 2, a 3, or a 4. And these would be individual x values that we'd have here. So I could roll once and get a 1, roll once, get a 2, roll once, get a 3, roll once, get a 4. So if I figure out my population mean would be I can roll a 1, 2, a 3, or 4. I have 4 choices to choose from. The mean I would get would just be a 2.5. Okay. So far, nothing that's really new. Here's going to be where the real change pops in here in a second. So if I'm talking about my standard deviation as well, sorry, my standard deviation, if I calculated that, would be 1.118. We're going to use that in a bit. Suppose that the tetrahedral die is tossed 3 times. So we're not recording individual tosses. What we're looking at is a sample of 3 tosses. So what we have here are samples. So everything we've done far has been really focusing on individual values. We've been looking at if I do something one time was the probabilities. Here we're looking at groups. So the sequence of numbers observed may be thought of as samples of size 3. So we may get a sample such as we roll a 1 3 times. We roll a 1 twice and then we roll a 2. We roll a 1 twice, then we get a 3. We roll a 1 and then a 2 and then a 1. We roll a 1 and then a 3 and then a 1. So there is a bunch of different combinations that we can end up with. So what we're seeing here is that these are all my samples and these are my means. Like I said, it's possible that I roll a sample that's all 1 and the mean of that would be 1. There's a possibility I roll a sample of 2 and then 2 ones. That mean would be 1.3. I might roll a 3 and then a 2 and then a 3. Or like I said, this one's the same event, but it just happens in different order. I could get a 2 and a 3 and a 3, or a 3, a 2, and a 3. So what this is doing is generate every possible sample I can get of a sample size 3. Oops. So we have every possible sample of size 3. And then we find all the means. And we have every possible mean for samples of size 3. So what we're doing here is a simulation because in the real world, if we collect several samples, we probably won't collect every possible sample that is in existence, but we can try to get as close as we can. So if I go through here and I take all these means, we got the 1, the 1.33, the 1.67, the 2.00, and we add all the way up 3.67. My last one is the 3. So if I added all of those up and then I divided that by my sample size, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that is going to be 39 different values that I got here. If I added up all those means and I divided by how many different samples I have with size 3, I should end up again with 1 point. Oops, sorry, 2 point. I should end up with 2.5. So just as a reminder, when I'm looking at just x's, so my population was I can roll a 1, a 2, a 3, or a 4. That had a mean of 2.5 and a standard deviation of 1.118. What we're saying here is that if I look at my mean of all my means, all sample means, let me add there, all means of samples of size 3, what we're getting is that we're going to get a mean again. So my mean of my means is going to be 2.5. We need a special way to denote this kind of mean because this mean and this mean are not exactly the same thing. This is just a mean for individual x values. This is a mean of means. We use a little subscript of x bar. So that should have been the notation. The notation for the mean of all of our means, all our x bars, is going to be mu x bar. If I went through and I found the standard deviation, that's going to be a little bit more work. We're not going to worry about that right now. But if I went and I had found that, the standard deviation of all of my means, that is going to be 0.6455. And once again, this is not the same standard deviation as this. This is a standard deviation of my population. This is a standard deviation of means. So we're going to put a subscript of an x bar on it as well. So the notation for the standard deviation of all values x bar is sigma x bar. So what we have done here is we took every possible sample that exists. I found every possible mean that those are going to make. So I have all the means of all my samples of size 3. And when I do take all those and I find their mean, that is going to be the mean of all my x bars, the mean of all my means. I can also find a standard deviation, which is the standard deviation of all my means, or the standard deviation of all my x bars. So this is a distribution. We got a bunch of means here. This is a whole. This is a whole sample size, or something like, or a whole population actually. But it's a whole set of data. We're going through that whole set of data, and we're finding a mean, and we're finding a standard deviation, and we're doing it the way we always did, adding up everything, dividing by the number we have, doing the standard deviation. We subtract the mean from everything, square it, do the summation, divide by n. Nothing has really changed from here and here. It's just the concept of what we're finding has changed. Okay. Before I go forward, let me go through that one more time, what it is we're really doing here. So this mean here is the mean of a population of x's, a whole bunch of data values. This standard deviation is just the standard deviation of a population of x values again. Now, the only thing that's changing here is that mu sub x bar, this is the mean. This is the mean of a population of sample means. Or we'd say x bar values. So the only thing that's really changed here is that one is just looking at individual data points. And what we did here is that we changed to, instead of individual data points, we're looking at samples. That's really the big difference here. And not just samples, but means of samples. So then when we talk about that standard deviation, this is a mean of means. So you take your bunch of means and you do a mean of the means. And then this is going to be a standard deviation of all those means. This is the standard deviation of a population sample. So every possible sample that exists is the idea here. Or once again, X bar values. Like I said, this is really the big difference that we're looking at, is that we did everything with individual data points. We had just X values. We had just people's IQs, just people's heights, just people's body temperature. This here now is we're talking about means. So it's like if I take samples of size 5, it is the mean IQ that sample has, the mean IQ that the mean IQ that sample has. It's the mean height that sample has, or the mean body temperatures that sample has. And we're taking those means and we're finding a mean of those means and a standard deviation of those means. Oops, almost. Okay. So one of the things that we had said was that when we initially were looking at the tetrahedrons, sorry, give me the wrong color here. The population had a mean of 2.5, but when I did the mean of the sampling distribution, so this is my mean of means, we also got 2.5. So one of the things we know is that if I did collect every possible sample of a certain size, that what we should expect is that the mean of the sampling distribution, which we denote as mu of X bar, is going to be equal to population mean. And what happens here is that because I'm doing samples, those when we collect a sample, that sample should be close to your population mean. Or your sample mean should always be close to your population mean. So what we have here is that we have a whole bunch of sample means that are very, very close to the population mean. So if we average out a bunch of samples and get a new mean, that is going to be even closer to your population mean, so close that they're going to be equal. And actually, like I said, if we collected every possible sample that existed, they would be equal. But like I said, that's not going to happen. But if it did in a perfect world, this is what we expect to be exactly equal. But it's close enough that we just say it is. The standard deviation of the sampling distribution. So standard deviation of the means is 0.6455. If you're talking about that population, though, the population standard deviation, so that was looking at the 1, 2, 3, and 4, the individual die rolls, so we got 1.118. So it's not very obvious about what the relationship is, but remember when we did these samples, or these means, we were looking at samples of size 3, right? Because we're collecting 3 points. Well, what we notice is that the relationship we do have is that the mean of my sampling distribution, or sorry, the standard deviation of my sampling distribution, so standard deviation of my sample mean, if I divide it by the square root of the sample size, or is it going to be the population mean divided population standard deviation divided by the square root of the sample size? That is too much to say. Essentially, we're getting to this. So the standard deviation of a sampling distribution, the standard deviation of means, sometimes called the standard error, is denoted by sigma sub X bar and is equal to the standard deviation of the population divided by the square root of the sample size. Okay, like I said, that one may be not so straightforward to see that relationship, where the first one we can. But like I said, somebody has found that relationship for us, so we're just repeating it. So like I said, this is when we have that X bar, this means that we're looking at the mean and standard deviation of a bunch of sample means. So we're talking about looking at things as groups. So just for practice, we're just interested in figuring out if we had a sampling distribution, what the mean and standard deviation would be. So among a certain college, the mean number of hours of television watched per week is going to be 10.5 hours, and the standard deviation is 3.6 hours. So mu is 10.5 and sigma is 3.6. So once again, this is just looking at individuals. So we know that this how we figure out this next part here. So a simple random sample of 16 students is chosen for their viewing habit. So we have a sample of size 16. So n is 16. What we want to know is we want to let x bar be the mean number of hours watched by the sampled students. And what we want to find is mu sub x bar and sigma sub x bar of your x bars. So what we're finding here is my x bars are going to be the means or the mean number of hours. Mean number of hours watching television. Or samples or groups of 516. That sample size is going to be important because it changes my standard deviation. So remember, this was individuals. So we're looking at x's here, and my x's represent as just hours. Numbers of hours watching television for an individual. So all we're looking here is all my x's are just individuals we looked at. Here we're looking at x bars, so they're means of sample. So what we know is that mu sub x bar is equal to mu. And we know that mu is 10.5. Therefore, mu sub x bar, the mean of all my means, is going to be 10.5. So the mean of my sampling distribution is this. Sigma sub x bar is going to be sigma divided by the square root of my sample size n. So the standard deviation of my sampling distribution is going to be 3.6, because that was my sigma, divided by my sample size of 16. So in that case, we know that's going to be divided by 4. So 3.6 divided by 4, it's just going to be 0.9. So if we had a distribution of x bars, the distribution of means for, and it has, like I said, the sample size matter for a sample of size 16 is, the mean is going to be 10.5. That's an easy one to figure out. And the standard deviation is going to be 0.9. Remember, this is looking at means. So it's telling me that if I take a bunch of different means, they're averaging 10.5, and they only vary from that center by 0.9. So we'll go through this one more time. So there's a slight change here. So the population has a mean of 6 and a standard deviation of 4. So this is just any population. I want to find mu sub x bar and sigma sub x bar for sample size of 25. And then I'm going to do it again for 50. Once again, remember that sigma sub x bar, or sorry, mu sub x bar is equal to mu. Sigma sub x bar is equal to sigma divided by the square root of my sample size. So for my first one, if I have a sample size of 25, the mean is still going to stay 6, like we have here, and the standard deviation is going to be the 4 divided by the square root of the sample size, or the 25. So that's 4 over 5, or 0.8. So like I said, sample size is important, and we're going to see why here. So if my sample size is now 50, well, mu sub x bar is still equal to mu. That doesn't change, and mu is still 6. Mean hasn't changed at all. However, standard deviation, that is going to change. Because now I'm going to take my sigma, my 4, and divide it by the square root of not 25, but 50. So square root of 50 is not a nice whole number. So I'm actually going to have to put in my calculator 4 divided by the square root of 50. I use different calculator because that one kept rounding the answer. That's going to be 2 times 1.414 divided by 5. Converted it. This is going to be approximately 0.57. We'll round it to there. So you see the standard deviation has changed. And this is going to be a key feature that we're going to see, talk about sampling distributions, is that sampling distributions tend towards the population mean. So that means that they head towards it almost to the point they may start making almost like a vertical straight line right above it when we're making these distributions. And that's because as my sample sizes get bigger, my standard deviations get smaller. So as n increases, standard deviation decreases. And what we're seeing here is that one of the things that we're looking at is that when we're talking about looking at this as a group, we would expect that a group of individuals, like let's say we're looking at IQ, we expect that they're going to be centered around 100, but they have a standard deviation of 15, meaning that I expect a widespread in IQs. So if I randomly choose people, I totally expect to find people who have an IQ of 70 and people with an IQ of like 101, and I expect to find people with an IQ of 130. Those are all expected because 15 is a high standard deviation. There's a lot of room for error. If I'm talking about groups, though, if I collect a group of 10 people and I test their IQ, the probability that a group of 10 people are going to have a IQ of 130 or a mean IQ of 130 is not very likely. Because, like I said, if we randomly collect those people, they should all, some of them are going to be at 70, some are going to be at 130, some are going to be around 100. And if we average those together, we're going to get something that's going to be close to 100. So those standard deviations are going to go down as we collect bigger and bigger samples because larger and larger samples are going to have less room for error.